Hi everyone! Today let's talk about section 3.5, Inverses of Matrices. We call that the n by n identity matrix is the diagonal matrix I with 1s on the diagonals and the other entries are 0. So this is the identity matrix. So for numbers, we have inverse, like 2 times 1/2 is 1. So this is the inverse of 2 is 1/2, right? How about for matrix? Can we find inverse of a matrix? Well, so if a matrix A and then 0 square matrix A has an inverse, then we have A times A inverse equals to the identity matrix equals A inverse times A. And it turns out not all square matrix has an inverse. Okay? And if there is an inverse, then the order of the multiplication does not matter. Okay? And you can see A times A inverse is the same as A inverse times A. They're both equals I. Okay? The next question is, how could we find the inverse matrix if it exists? Well, we can think about the A inverse as a set of elementary row operations that transform A to I. Then the same operations acting on I will give us A inverse. Why is that? So you can see, okay, think about, we have the adjoins, we have matrix A adjoins the matrix I. If we have a set of elementary row operations, the effect is like multiply A inverse on the left. Now what happened? Okay, so when we multiply it, we get A inverse times A, and here we get A inverse times I. But we know A inverse times A is actually the identity matrix, and A inverse times I is A inverse. So now you can see this is going to be the A inverse. And this is how we do it. We write down the matrix A adjoined I, and then we do a sequence of elementary row operations so that we can get reduced echelon form. So we get I on the left, then the right side is going to be the inverse of A. Okay, so now let's look at this example. So this is the matrix A. We want to find the inverse matrix. So what we do is we first write down the A. Adjoin with the identity matrix. Okay, and then we perform a sequence of elementary row operations. So remember, what's the Gaussian elimination? We want to make this guy 1. It's already 1. Great. And then we want to use it to kill the entries below it. How do we kill this 2? We use minus 2R1 add to R2. How do we kill this negative 2? We use 2R1 add to row 3. Okay, now let's see. The first row stay the same. And then now 2 minus 2 is 0. Minus 1 minus 2 is negative 3. 3 minus 2 times minus 1. So 3 plus 2 is 5. 0 minus 2 minus 2. 1 minus 0, 1. And this is 0. Alright. And then for the third row, let's see. Negative 2 plus 2 is 0. And then here 2 minus 2 is also 0. Negative 2 plus 4 is 2. 2 plus 0 is 2. 0 plus 0 is 0. 0 plus 1 is 1. So far, so good, everyone? Wow. Okay, what is next? Well, you can see this, we already have a stair shape. So this is the echelon form. So next, we're gonna, we want to get reduced echelon form. So how do we do it? We want to get the 1 here. Okay, so how do we get the 1 here? By the way, don't touch the first row, because if you want to add the first row, you would create non-zero entries there. We don't want to do that. And actually, in this case, we can only divide it by 2. We cannot avoid fractions if we want to get a reduced echelon form. Okay, so this is, let's see, first row stay the same. And then second row stay the same. Third row divided by 2. Okay, now after we get this guy 1, and then we want to use it to queue the entries above it. And now what happened? So how do we queue the -1? We use row 3 add to row 1. -1 plus 1, 0. 1 plus 1, 2. 0 plus 0, 0. 0 plus 1/2, 1/2. And then how do we queue this 5? We use -5 R3 add to R2. And then 0, -3. Okay, 5 minus 5 is 0. -2 minus 5 is -7. 1 minus 0 is 1. 0 minus 5 times 1/2, so -5/2. So far, so good? Okay, what is next? Well, next we want to make this guy 1. And how to make this guy 1? You cannot touch the first row because you will create non-zero entry here. So here we have to divide it by -3. So let's see. Okay, let me make this smaller. Okay, let's see. Let me choose those and make it smaller so that I have in more space. Oops, I forgot to choose this one. It's okay, I can draw it. Oops. All right. Okay, now let's go up here. We want to divide it by 1. We divide by 3. So 0, 1, 0 divided by -3, so 7/3. This is -1/3. Negative become positive, and then 5/6. All right. Okay, now we can use it to queue the entry above it. So queue this one. We can do minus row 2 add to row 1. 1 minus 1 is 0. 0 minus 0 is 0. 2 minus 7/3. 2 is like 6/3 minus 7/3, -1/3. And then with 0 minus -1/3 become positive 1/3. 1/2 minus 5/6. 1/2 is like 3/6. 3 minus 5 is -2. -2/6 is -1/3. Alright, and next second row stay the same. Third row stay the same. Now, can you see this is the identity matrix? Then this guy is the inverse. So A inverse is -1/3, 1/3, -1/3, 7/3, -1/3, 5, 6, 1, 0, 1/2. Okay? So this is the inverse. Okay? And this is how we get the inverse. We first get if A is 3x3 matrix, we want to get a 3x6 matrix. We use A adjoined the identity matrix. And the first thing we do is to make this 1, make the 1, 1 entry 1, and then queue the entries below it. And then usually next step should be make this one, make the 2 2 entry be 1, and then kill the entries below it, right? And then the next steps, we're gonna make this one, make the 3 3 entry 1, and then we want to kill the entries above it. Okay, and then the next steps, we want to make this guy 1, and then kill the entry above. And then you can see finally we will get an identity matrix on the left. If the inverse exists, we can get identity matrix on the left. Okay? And the common mistake is, like I said, when students try to make this guy 1, they touch the first row, which will create non-zero entries here. So just be careful, okay? You want these guys stay zeros, okay? So this is example 1. Let's continue. Okay. Questions. What happens when there is no inverse? Well, it means, well, when we try to do a sequence of elementary row operations, we cannot transform A into the identity matrix, and we will get stuck somewhere in the process. And let's see what happened with this matrix. So we have A, adjoined with the identity matrix. Okay, now first thing, make this guy 1. Oh, it's already 1. Awesome. And then we can use it to kill the entries below it. So minus 2 R1 add to R2 and minus 2 R1 add to R3. Alright. So in this process, I hope you can find, because there are a lot of different ways to do the operations, but you want to find the easiest way, because sometimes if you find an easier way to do it, it may just take you 10 minutes, 15 minutes to complete the problem. But sometimes if you pick the wrong operations, and then it might take you an hour to do it. Okay, and yeah, your exam has limited time, so you gotta make sure you try not to make mistakes. Okay. Okay, so first row stay the same. Second row, 2 minus 2 is 0. Minus 1 minus 2, negative 3. Minus 1 minus 2 times 2. So minus 1 minus 4, which is negative 5. And then 0 minus 2, negative 2. 1 minus 0, 1. 0 minus 0, 0. Okay. Third row, 2 minus 2, 0. 2 minus 2, 0. 4 minus 2 times 2, 4 minus 4, 0. 0 minus 2, negative 2. And then 0 minus 0, 1 minus 0, 1. Oh, do you see what happened? This is action form, okay? But can you see this guy? This guy is 0. But in order to get the identity matrix, we at least need a non-zero number, right? We need a non-zero number so that we can divide it, and then we can get 1 to get 1, right? But here, because it's 0, we get stuck. So this matrix has no inverse. Okay, so this is what it means. We cannot transform the matrix A into I, and we get stuck somewhere. So here we get stuck because this guy is 0, well, we cannot get 1, right? Okay, so this is example 2. Now we have finished example 1 where we can find the inverse, and example 2, and we can see there is no inverse for it. Alright, let's continue. We call that when AX equals B, A is an n by n matrix, it has a unit solution, then the reduced echelon matrix is I. Okay, and let's see why these two results are related. So consider A is n by n matrix. Given the linear system AX equals B, in the case of unit solution, we want to find the reduced echelon matrix. We perform Gaussian elimination. So we first form the augmented coefficient matrix. We use A adjoined with the vector B, and then we perform row operations. So by a sequence of row operations, we get this is the identity matrix. So this is the reduced echelon matrix, right? And then this guy is the solution. Okay, so it means x1 is b1 prime, x2 is b2 prime. So this is the solution. This is our unit solution. Okay, now look what happened. So we can think of this sequence of elementary row operations. The effect is like multiplying A inverse on the left. Okay, so A inverse times AB is a shorthand notation for A inverse times the linear system AX equals to B. And now what happened? If you multiply by A inverse on the left, on both sides, A inverse times A inverse times B, A inverse times A will get identity matrix. And so you can see identity matrix times X is A inverse times B. So X equals A inverse times B. This is the unique solution. Okay? And what is the good thing about this? Well, so imagine if we have a lot of linear system, and if we want to change different B, then if we use this form, X equals A inverse times B, we don't need to do a lot of Gaussian elimination. And every time with a different B, we can just use A inverse multiplied by that vector, then we can get the solution. So we don't need to perform the elementary operations like Gaussian elimination every time when we have a different vector B. Okay? So we have the following statements are equivalent. First, A is row equivalent to the identity matrix. Yeah, because we can show the A, we can perform elementary row operations so that we can get a reduced echelon from the identity matrix. And next, inverse exists, right? If A is equivalent to row equivalent to the identity matrix, then the inverse exists. And we know the linear system has a unit solution for any B. Okay, so these three statements are equivalent. Okay, next big questions. When does A has an inverse? Okay, when does it has an inverse? Okay, for numbers, we know for numbers, if we have like a P over Q, we need Q is not 0, right? And so this is like the criterion for it, right? So for the inverse exists, okay? Let's say n is a number. We want to have 1 over n exists. Then we need what? We need n is not 0 because 0 does not have inverse. So we want to figure out for, how about for matrices? Is there any requirement for matrix so that the inverse exists? And it turns out the determinant is not 0, then the inverse exists. So what is the determinant? Okay, let me show you here. So let's start with a 2 by 2 matrix A in general. Okay, And let's say, so this is the matrix A. We want to find the inverse. So we want to put A adjoint with the identity matrix. And let's see how to find the inverse. Okay, first of all, we want to suppose A and C. So we know one of them is not zero, right? Because if one of them is zero, well, then we know that this guy is not row equivalent to the identity matrix, because you cannot get the one here. Okay, in order to get the one here, you need A or B. One of them is not zero. Okay, so we know A is not zero or C is not zero. Okay, one of them is not zero. Okay, so let's assume A is not zero. Okay, if C is zero, it's okay. You just interchange two rows, then C is in the position of A. So let's assume A is not zero. Okay, now let's see if we assume A is not zero, then what happened? Let's perform Gaussian elimination. So we want to make this entry 1. How do we do it? We can divide it by A, and because we assume A is not zero, so it's okay to do that, right? When we divide it by A, we get 1, and then B over A, 1 over A, 0. And then next, we want to use this one to kill the entry below it. So the operation, what operation shall we do here? We use C times negative C times row 1 add to row 2. Okay, now let's see what happened. The first row stayed the same. Second row, C minus C is 0. D minus C times B over A. 0 minus C over A. 1 minus 0. So this is what we get. So far, so good, everyone. And let's simplify it. This guy, if we take A to be the common denominator, we get AD minus BC on top, right? And then the next steps, what we're gonna do, we want to make this guy 1. Okay, how do we make this guy 1? Well, we multiply by the second row. So multiply the second row by A over AD minus BC. And when we multiply this guy, we need the denominator is not 0, right? So in this operations, we need AD minus BC is not 0. Now what happened? We get 1, B over A, 1 over A, 0. And then we get 1, right? Okay, so, and the next guy, we can see A over AD minus BC times negative C over A. You can see the A cancel. So this guy, we get minus C over AD minus BC. And next one, we have 1. Okay, so become A over AD minus BC. Okay, next, we want to use it to kill the entry above it. So what operation we should do here? We use minus B over A times row 2 add to row 1. Okay, now let's see what happened. We have, okay, second row stay the same. Okay, and then, so And then here b over a minus b over a becomes 0. And then the next one, we get 1 over a minus b over a times negative become positive, c over ad minus bc. And then the next one, 0 plus negative b over a times this guy. Well, b over a times this guy, a over ad minus bc. Can you see a cancel? So what do we get? Okay, so 1, 0, 0, 1. This guy is actually minus b over ad minus bc. And here we get minus c over ad minus bc. This is a over ad minus bc. Okay, but then how about this guy? Okay, let's calculate it here. So let's see. We have the common denominator a, ad minus bc. The first fractions we multiply by ad minus bc. Next one we have bc. Oh, you see bc cancel, and then we have ad over a ad minus bc. Do you see a cancel? We just get d over ad minus bc. So this is d over ad minus bc. Okay, so then this guy is the inverse of a. Can you see all of them has the denominator ad minus bc? We can actually pull out the denominator, and then what's left? We have d minus b minus c and a. So this is the formula of the inverse matrix for 2 by 2 matrix A, okay? And in order to have the inverse exist, we need what? We need this guy, the denominator is not 0. So that's why the determinants of A, we define it to be AD minus BC. Okay? And think about, so this is A, AD minus BC is like cross multiply, but you subtract. So AD subtract BC. So cross multiply, but you subtract. So this is how I remember the determinants. And how you remember the inverse? You use 1 over the determinants, and then, okay, what happened? So let me put down a here. So A is A, B, C, D. Okay, so how do I remember this formula? You use 1 over the determinants, AD minus BC, and then what happened? You look at A and D. So you switch A and D. Now you put a D here and you put an A here. For B and C, you add a minus sign. Okay, so how do I remember this? I think about we switch AD. Okay, so switch AD and then add a minus sign to BC. Then you can get this formula. Okay, so this is the formula for the A inverse. Okay, and the determinants for 2 by 2 matrix is AD minus BC. So the notation for it, you either put determinant and then you have the brackets. By the way, brackets means this is a matrix. Sometimes parentheses also means this is a matrix. So for example, you can put, so these two forms, they all represent matrices. But if you put like the absolute value means determinant. Okay? So the absolute value means the determinant. Determinant is a number, and matrix has size m by n, right? And usually for determinants, we must have a square matrix, then we can talk about its inverse and its determinant. Okay? But for the notation, absolute values of a matrix is like determinant. Okay, and for 2 by 2 matrix, we use AD minus BC. Okay, so let's continue in video part B. See you soon.